Assalamu alaikum wa rahmatullahi wa barakatuh. Today, inshallah, we'll discuss together the experiment number 7, which aims to define or determine the parameters of a separately excited DC motor. Simply, we described in lectures the mathematical model of separately excited DC motor. As you can see here, this is the equivalent circuit. We have resistance and inductance of the armature winding, and we have field winding, and also we have some parts representing the dynamic equations, which is a mechanical part of the motor. So this is the mathematical model that we have described before, and this is the electrical model, the first equation, LA multiplied by d by dt for armature current plus RAIA plus equal VA minus E, which represents the electrical model of DC motor, and the dynamic equation, which represents the mechanical model of the DC motor, which is simply J d omega by dt plus B omega equal electric torque minus load torque. And you know, these are the definitions of the electrical and the mechanical quantities in the equation. And also we described in lecture how to convert this model to Laplace transform in order to obtain a mathematical equation and transfer function for the motor. So finally, we have a transfer function like which is shown here in equation number 11, and we can represent the DC motor using this block diagram. As you can see, this is the output speed, omega m, and we have Km, which is the motor constant, and this motor constant converts omega to equivalent corresponding voltage. The reference voltage is or the supply voltage if the source is subtracted here from EMF, and this will be the difference in voltage when we divide by the electrical part or multiplied with the electrical gain will give you the electrical current. When you multiply current by motor constant, you will get the electrical torque, and you know relation of electrical torque, torque electric minus torque load equal J d omega by dt plus B omega, blah, blah, and so on. So this is the part which represents the mechanical model, and this is again the speed of the DC motor. So this block diagram, as we described in our lectures, represent the separately excited DC motor electromechanical model. Right. The aim of our experiment today is to determine these elements, determine these parameters. We have here parameters like R, like tau, electrical time constant, like Km, motor constant, like B, motor friction coefficient, like tau, mechanical, which is mechanical time constant, and you know the relation of tau depends on the motor inertia, as we defined it before in equation number 8. Tau mechanical equal to inertia divided by the motor friction coefficient. So, why we need to determine these parameters? Mainly, in order to control any DC motor, we have to include this model or apply a controller to this model or transfer function in order to control the motor. So, simply, we need to apply at this portion a PI controller, for example, in order to control the machine voltage to achieve a certain speed. And this is what we are going, inshallah, to describe next experiment. How can we do that without getting the motor parameters? It's impossible. So, in order to control the machine speed, we need first to identify the motor parameters. So this is the main aim of identifying the machine parameters. In order to identify these parameters, we will make many tests today. The procedure will start with some tests like preliminary test. In this test, we need just to fill the nameplate data from the generator, PC generator, in table 1 here. And there is just the data we obtain from our lab, like each experiment. We have nominal voltage, we have nominal current, we have nominal field current and motor speed, and also the rated power. Also, it is required here to get the multimeter measurements of the machine resistance. So we have many windings in our motor. You know, we have coil number A, we have coil number B, and coil number C. So it is required here to calculate or to measure the resistance for each coil. So simply, we will apply the multimeter to each winding for coil number A between two terminals A1 and A2 and measure the equivalent resistance of the winding number A. The same is also for winding number B and C. This is the first task. Second task is to calculate the armature resistance. Armature resistance is nothing but the series resistances of the three coils A, B, and C. This is if we are going to connect the three coils in series. So the total armature resistance here can be represented by the sum of three quantities of resistances we got in table number 2. And also we can use our multimeter and make this connection in the motor. So we just will connect the coils in series. We have coil number A, it will be connected in series with coil number B and also in series with coil number C. And between the beginning terminal and end terminal of the coils, we will measure the resistance by using multimeter. So by this way, we can obtain the value of armature resistance. The third part, or part number C, we need to calculate the armature time constant. Armature time constant, which we have defined before in the mathematical equation. Electrical time constant is nothing but inductance divided by the armature resistance. So how we can calculate the electrical time constant? Here we need to make a test by connecting the machine, like in figure number 4. So simply, this is the armature of our motor that we need to calculate the or measure the time constant. We are going to connect the coils A, B, and C in series, like in the figure here, and we will measure the armature current, and also we will measure the applied voltage to the armature. So we have channel B to measure current and channel A to measure the input voltage. And we will connect these channels of the isolation amplifier to a Brophy-Casi, and then we can get the results on the computer. Also, we need to connect the tachometer to measure the speed of the machine, and also we will connect the torque output from torque control unit to channel number B for the sensor Casi in order to measure the torque. And as you can see here, the tachometer is connected between the DC motor and the braking load. So this is the wiring diagram we are going to connect and use to test, to calculate or to measure the electrical time constant. So these are the steps here. We will adjust the torque control units on these values like we make each experiment. For example, we will set the torque scale to 10 Newton meters, and then we will select the load to manual or external for mode position number 1, so it will be manual. And we will set n minimum to be 10% of the machine defined speed, and this is to prevent the motor speed to drop below 10% of the RPM of the scale defined in the torque control unit. And we will set M max to 60%, which is the maximum allowable torque of the 10 Newton meter. So the torque here will be maximum, will be 6 Newton meters. And don't forget to connect the thermal protection terminals. We will adjust the amplifier, the isolation amplifier. For the voltage, we will select a ratio 1 to 100. And for the current, we will select the ratio of 1 volt per ampere. And we will run the BC chassis and define the channels, channel A, UA1 for applied voltage, UB1 for rotor applied voltage UA1, armature current UB1, rotor speed UA2, and UB2 as a machine torque. For definitions of all of these channels, we will select average value definition. And you remember previous labs, we were dealing with a synchronous machine and induction machine, and we defined current and voltage all of time as RMS values. However, here the test today will be on DC motor, so we can define all of quantities as average values. Then we'll define the equations of each term. We divided the voltage by 100 using amplifier, so we have to multiply channel UA1 by 100 to return the same value of A, and IA as UB1 because we don't have any ratio here. And for the speed, the tachometer itself has a ratio of 1000 RPM equivalent to 1 volt, so we will multiply the voltage value, which is representing the machine speed, by 1000 to give the actual RPM, and the torque load will be the same without any ratio. Then we will select the setting icon, and to activate the measurement parameters, we will select automatic recording, and the measuring interval, this is for the display, is 1 millisecond with number of 2000 points. So we will measure for 2 seconds. Why we will make that? Because we are going to make or to observe a curve in order to calculate the electrical time constant from this curve. So we need this period, 2 seconds, with measuring interval 1 millisecond, and each and the interval will include 2000 points. So 2000 points multiplied by sampling rate 1 millisecond will give you a period, or a total period of 2 seconds. Also, from display of chassis, we have to define the x-axis as time and the armature current on y-axis. So we are going to observe the current waveform. After the reviewing the connection, we will make this procedure in order to get the time constant. First, make sure the switch is off and DC supply voltage control knob is at 0. Then gradually we will increase the DC supply voltage to reach to 20 volts. So this will be the applied voltage on the armature winding. Then we will start recording by press F9. Then just after pressing F9, turn on the switch immediately don't wait more than measuring time. This means you have to immediately turn on the switch after pressing F9. This because we need to capture the current waveform during a period of 2 seconds. So don't wait the 2 seconds and press and turn the switch on. The interval will be ended and you will not record anything. So it's better to press F9 while your hand is on the switch to turn the switch on. After that, move the switch off and reduce the supply voltage to 0 again. Then switch off the DC supply. Then we are going to save our CASI file and keep it open. And we need now to report the value of armature time constant. How we can do that? Simply, this is a curve we are going to have. Actually, we will get the curve from interval t equal t1. Why, شباب? Because when we was in this part, when we were in this part, the supply was connected to the motor. So we switched the motor off, which means the current will be reduced until reaching 0. The definition of time constant for any circuit, we can calculate the time constant by using 2 different ways. Either the time required to reach the steady state, all of this time, when we get the value of 0.63 of the maximum value, which is this value here, this time will represent the electrical time constant. So for turning on, the time TE here represents the electrical time constant. But we will make the test during turn off, so it means it will be that time. So we need to calculate the current from this portion by 63% of the maximum current and find the value of 1 minus 0.63 multiplied by the maximum current, or 37 of the current, and this will give you the time from the instant of disconnection to the instant of that time, and this will be the interval tau E. So this is the electrical time constant test. After that, we will make the motor constant test. Again, please here. Now, this will be the procedure, how we are going to take the results from the test in order to obtain the time constant value. So at the end of this lab, I will provide you with the data or curves, and you have to calculate all of the parameters required. Right. Next parameter, which is motor constant Km. How we can measure Km? There is a test also to measure the machine constant. So simply, we will have another procedure. Remove all recorded measurements from CASI. We have to define new quantities. Connect circuit diagram shown in figure 5. We will describe the figure now. We will use the 0.24 volt supply, 20 amps, which is a small one. We will remove it and replace it by the variable DC supply, 40 to 250 volt, 10 amps supply, because we need to increase the voltage here. In addition, we have to connect the motor field circuit E1 to E2 to the DC supply, variable DC supply 0 to 250 volt, 0.5 amps. So this is our connection here. So for now, the armature circuit is the same. We have measured the armature current and armature voltage with the same quantities used before in the previous test. And we are going only to place the supply to be 250 volt 10 amps DC power supply on variable شباب from 440 to 250 volt. And the extra here, we are going to connect the field winding of coil E1, E2 to a supply of 0 to 250 volt. So take care, the field current of the machine is rated at 0.24 amps. So we have to check the value as the procedure will discuss with us here. So simply we will connect the configuration of figure 5 and make sure that both of these supplies at 0 and off, the position at 0 and the supply switch is turned off. Then we will define some parameters on CASI. So we will make a definition for the EMF. So EA equal to VA minus RAIA. Actually, we defined before RA because we calculated or measured it using multimeter in the beginning. And we have a channel for IA and VA. So take care when you enter these parameters to CASI, you have to use the same symbols that you have defined the channels in order to make the computer understanding your equations. And so this is the EMF and the motor angular speed omega m as Nm, which is the motor speed, divided by 9.55, which is the same relation between converting its speed from RPM to radian per second scale. So replace RA by its value measured earlier. So we are going to substitute the formula VA, which is a defined channel, minus the value of RA multiplied by the current channel name. So this will be the equation of EA. Simply, if we have EA and we measured already omega m, so we can substitute in the equation EA divide omega m to get the motor constant. However, this needs the procedure we are going to describe now in order to calculate the machine constant. So we will double click again to measuring parameters and select manual recording option. And from display, we need to measure or record the curve where omega m is as x-axis and EA is at y-axis. So the horizontal axis will represent the machine speed and the vertical axis will represent the induced voltage. Gradually apply the DC field supply voltage to reaching rated field current of 0.24 amps. So we will increase the field current from 0 to 0.24 amps, whatever the value of applied voltage. So we'll start with the voltage knob from 0 up till reaching 0.24 amps. Then move the switch on position and gradually apply the DC motor power supply voltage to start the motor till reaching the speed of 1000 RPM. So start increasing the voltage gradually up till reach to 1000 RPM. Then press F9 to record the readings. Gradually increase the supply voltage to reach to a speed of 2000 RPM in 5 to 10 steps. So we will press F9 from 5 to 10 steps and measure the points manually or record the points manually. But take care when we will make this test, we have to wait at each speed for 1 or 2 seconds and then press F9. After changing the volt, we have to wait a bit and then press F9. This is to reach to steady state, to be sure that the machine speed is reached to the steady state of the new applied voltage. Step after that, reduce the supply voltage to 0 and move the switch off. So after drawing the curve or recording the curve from 1000 to 2000 RPM, we will disconnect the supply and return the supply knob to 0 again. Save your CASI and calculate Km as the slope of the recorded measurement. So after making the test, we will have a curve between E and omega m. The slope of this curve will be the machine constant Km. So now we could calculate RA, we could calculate electrical time constant and the motor constant. We still need to calculate two different parameters, which are the machine friction coefficient and mechanical time constant to calculate the motor inertia. For the viscous coefficient or viscous friction coefficient, will make another test. Remove all record measurements from the CASI file. From parameter formula, we will define a new quantity to define the electromagnetic torque, which is the electrical torque. We already measured a torque. This measured torque is the shaft torque or the machine output torque. However, we need to measure or calculate the electrical torque. So simply, electrical torque is nothing but machine constant multiplied by the armature current. We already calculated the machine constant and electrical current during test will be measured, so we can define electrical torque in that way. And we will define another equation or delta T, which is the difference between electrical torque and the mechanical torque. So this part of the equation now will represent torque electric minus torque load, which is equal to J d omega by dt plus B omega. So this term will represent the sum of other two terms. One term will depend on the speed, and another term depend on the derivative of the speed. Then double click to the setting icon to activate the measurement parameters and select the manual recording option and display in order to record the delta T with omega. So we'll define omega as the horizontal axis and delta T as the y-axis. Then move the switch on position and gradually apply the DC motor power and start motor till reaching to a speed of 1000 RPM and press F9. So we will press F9 when we reach to the speed of 1000 RPM like we have made in the previous test. After that, gradually increase the supply voltage to reach to 2000 RPM again. And also it's in 5 to 10 steps. And it's written here clearly. Press F9 to record the reading. After each adjustment, wait for 3 seconds. 3 seconds is long time. This is to be sure that the term of d omega by dt is 0. This again to be sure that the term d omega by dt is 0, because if d omega by dt is 0, this means delta t at this time will be only equal to b omega. So the slope of this recorded curve will represent the machine viscous coefficient, and the inertia will not be considered because the curve will not consider the machine d omega by dt. It will only consider the steady state case. For that, we have to wait for 3 seconds. Then again, we will reduce the supply voltage to 0 and move the switch off position to be in safe, and then we can calculate B from the slope of the recorded curve. So up till now, we could get the, from the mechanical parameters, we could get the machine viscous coefficient. In order to calculate inertia, we need to calculate mechanical time constant. So we need another test to make the mechanical time constant test. Simply remove all recorded measurement from the CASI file again, double click on setting icon to activate the measuring parameters, select the automatic recording. So we will make it automatic recording in this part. We will not use F9 or press F9 many times for each reading. It will be automatic. And then set the measurement interval at 1 millisecond with a number of 2,000 readings. So it's expected to have an interval of 2 seconds. Simply, from display also, we will define the time on x-axis and speed on y-axis. What is the need here? We need here to record the speed at the from the instant of disconnecting supply at a certain motor speed up till reaching to 0. This is called deceleration test. The aim of deceleration test is to calculate mechanical time constant, and by means of viscous friction coefficient, we can calculate the motor inertia. So simply, the procedure again, we will turn on the supply and gradually increase the motor supply voltage after reaching to 2,000 RPM here, because we need to disconnect the supply of the motor at a point where the previous point is rated speed. So we'll adjust the speed at 2,000 RPM and we'll start recording by pressing F9, but immediately we have to switch off the switch. We have to switch off the supply. Why? Because we need to record the machine speed while it's degrading from the 2,000 RPM up to reaching to 0. So simply, we can make a curve like we have made with the current and measure the time constant, the mechanical time constant, in the same way by considering the time constant of 63% of the value. So at value of 2,000 RPM, the value of 0.37 multiplied by 2,000 will give you the value of 37% of the rated speed, and you can calculate the time from this value to the 0 speed like we have made in current measurements. So this is simply the procedure we are going to make in this experiment. Finally, you need to fill the report with the required data here. It's very important note. All of the parameters we have, we will calculate from this experiment are going to be used in the next lab. So we expect to have all of these values by the next lab, and next lab will be based on MATLAB Simulink. So you have to calculate all of the motor parameters and be ready for the next experiment, because all of the experiment will be based on the parameters you are going to calculate from these tests. Thank you, and see you in the experimental test.